Alrighty, the system's turned on. Let's get started. Okay, so on the Tuesday lecture we finished off on this slide where we'd just gotten to the point where we're talking about a binary number system. So we're learning that we currently use a decimal number system in everything that we do, but it's an arbitrary choice, and other choices are better in other situations. And in digital circuit design, a binary number system is what we need because we only have two possible states on and off, so we can only have two digits in our number, 0 and 1. Here is the first 16 binary values, and you'll just need to get quite familiar with them over this course. And if you can automatically say, for example, I tell you 10, you can automatically tell me that 1010 is 10 in binary. That'll help you a lot as you go through the course. All right, but of course we'll need to translate back and forward all the time. And for longer numbers, you won't necessarily be able to look at the binary and know automatically what the decimal equivalent is. You'll need to work it out. It's actually, because it's a weighted number system, it's actually quite easy to work out the value of a binary number just by remembering what the weights are for each column. So for example, in decimal, if I told you 79, or 79 actually, if I gave you the decimal number 79, you would know that the 9 is in the ones column, so it corresponds to 9 items, and the 7 is in the tens column, so it corresponds to 70 items. So altogether you have 79 items. Same thing in binary. We simply write down what the weightings are of each column, and they're all powers of 2. So another thing you'll get good at in this course is knowing what all the powers of 2 are. So 2, 4, 8, 16, 32, 64, 128, and so on. And each of those powers of 2 represents a different column as you move from right to left in a binary number. So each column is a power of 2, just like in decimal, each column is a power of 10. So 2 to the 0 is of course the ones column, 2 to the 1 is the twos column, 2 squared is the fours column, 2 to the power of 3 is the eights column, 16's column, so on and so forth as you move along. And then going the other way to the right of the decimal point, now it's negative powers of 2. Just like in decimal, we talk about negative powers of 10, so a tenth, a hundredth, a thousandth. In binary, we talk about negative powers of 2, so a half, a quarter, an eighth, and so on as you go from left to right after the decimal point. So, write down what all of the weights are for each column. So, what I've just told you, 1, 2, 4, 8, 16, 32, a half, a quarter, an eighth, so on. Then let's write down our binary number now, making sure that the zeros and ones line up with the appropriate columns. And just like in decimal, if I have a 9 in the tens column, then I know it's 9 lots of 10, so 90. In binary, if I have a 1 in the fours column, I know it's 1 lot of 4. If I have a 1 in the ones column, it's 1 lot of 1. If I have a 1 in the 32's column, it's 1 lot of 32. So I simply add up the weights of each of the columns that have a 1 in them, and that will give me my number. Obviously, 0 lots of 16 is 0, of course. 0 lots of 8 is, of course, 0. So we don't need to worry about those columns that have a 0 in them. We only need to worry about those columns that have a 1 in them. So we have 1 lot of 32, plus 1 lot of 4, plus 1 lot of 1, plus 1 lot of a quarter. And there is our number in decimal. So if you have a look here, I've got a little tiny 10 as a subscript to a number, and that's telling me that it's a decimal number. If I have a little subscript of 2 to the number, it's telling you that it's a binary number. So normally when you write down the number, the number system that we're using will be sort of clear from the context, and you'll be able to guess whether it's a binary or an octal or a hexadecimal or a decimal number. But where it's unclear, always put in this little subscript to tell you what is the actual number system that we're using right now. Because 1, 0, of course, if I don't give you any context, it can mean 10 if I'm using decimal, or it can mean 2 if I'm using binary. Okay? So if you're unclear, this little subscript tells you which particular number system we're using right now. All right, so we need to go the other way sometimes too as well. So we might have a decimal number, an ordinary number, and we want to write it in binary. So we actually do the reverse procedure from what we've just done. So we write down the weights of each column, and then we figure out which combination of columns we can use to add up to that number. All right? So there's a little bit of practice to get good at this, to get quick at this, But let's write down all of the weights of the columns. So the number is a whole number, 49, so we don't need to worry about columns to the right of the decimal point. So let's just write down all of the columns to the left of the decimal point and what their values are, 1, 2, 4, 8, 16, 32, 64. Now we need to add up to 49. So what combination of these numbers add up to 49? That's what we need to answer in order to write down the binary number, the binary value, a representation of the quantity 49. And in this case, we need one lot of 32, one lot of 16, and one lot of 1. And that will add up to 49. Everything else that we don't need, we put a 0 in that column. And then finally, we have our binary number. So the shortcut, or the way to think about it when you're doing this, is to say, okay, my number's 49. I need to get, first of all, I need to start with the column that's the biggest value that is less than 49. So the biggest value less than 49 happens to be 32. So I take 32. And then I say, okay, what's left over? So if I take 49 and I subtract 32, I've got 17 left over. So I need to make up 17. What's the biggest number that's less than 17 of all of the columns that I've got there? And it's 16. So I'll choose 16. So I wanted 17, I've got 16, so I've got 1 left over. And I say, okay, so what's the column for 1? And that's clearly just the 1, a 1 in the ones column. And that's the process you go through step by step to convert from a decimal to a binary. And you'll get really quick at doing that, particularly for the smaller numbers as you go. That's the process. And in the tutorial 1, which you'll be able to start doing after this lecture, there's lots of questions in there for you to practice this, going from decimal to binary and back binary to decimal again until you get quite familiar with it. All right, so again, 49 to the base 10, 49 to the base 10 is equivalent to 110001 to the base 2. They're the same number. Okay, so time for you guys to have a go. What I like to do in this lecture is every now and then, once I've taught a new concept, is you guys just to have a go at doing it yourself so that I can see if there's anything I need to go over again and so that you can see if there's anything you need to go over again, because watching it while I do it is the suboptimal way to learn. Having a go at it yourself is the best way to figure out whether you understand it or not. So have a go converting the first one to decimal, the second number, which is already decimal, converting it to binary. And if you feel confident the last one, but don't worry if you can't do the last one, I'll give you some tips in the next slide for how to do fractional parts a little bit more easily. All right, while you're doing that, has anyone got a question? Put your hand up if you want me to come up and help you with anything that we've just covered. No, it sounds like it's all good. Looks like you're all not having too many problems with that. Who wants to shout out the answer to the first one? 189 and 3/8. Does everyone agree with that? 0.375. Yep. Either is. Anyone else got a different answer? No? All good? So here's what we did. Simply write down all of the weights of all of the columns. 1, 2, 4, 8, 16, 32, 64, 128 as we move left of the decimal point, and a half, a quarter, an eighth. And again, you could do it in the half, the quarter and the eighth. You can do that in either fractions or in decimals, which both are, of course, the same, so that's totally fine. And then we add them all up, 128 plus 32 plus 16 plus 8 plus 4 plus 1 plus 0.25 plus 0.125, and we get our final answer, 189.375. Okay. Any issues with that? Anyone not see how I got that number? Okay. All right, the next one's easy. What's 9 in binary? Perfect. That was an easy one. So again, the biggest number that's smaller than 9, that's a column weighting, is 8. And then we have 1 left over, so we need a 1 in the ones column, and the other 2 columns in the middle get 0. So 9 is 1001. Alrighty, now this one is a bit more tricky. So we have, first of all, the 9 is obviously easy because we did it, the 9 part we just did in the previous question. The new bit is the fractional part. And it might be less, certainly for me it is, less obvious to, in my head, add up which fractional parts give me 0.8125. It's slightly less easy than it is to do it with whole numbers. But again, the process, the theory is exactly the same, just takes a little bit longer. And it's perfectly fine to do it this way. So what's the biggest fractional part that's less than 0.8125? And of course it's 0.5. We subtract that off, we say what's left, and then the next biggest bit is 0.25 and so on and so forth. So that's one way to convert with for the fractional part of a decimal number to binary. Everyone good so far, so good? All right, there's another method you can use, which is a sort of an algorithm, a turn the handle algorithm that you can use if you wish. Up to you. So I'll go through the algorithm first and then I'll give some intuition to why it works. So what we do is we start with the decimal number and we repeatedly multiply it by 2. And each time we multiply it by 2, we look at what the integer value is, so the value in the ones column, and we use that for our decimal, for our binary number. So let me show you with an example. So 0.188. So I've got a fraction, 0.188, and I need to convert that to binary. So first thing is I multiply it by 2. So 0.188 times 2 happens to be 0.367. Now 0.367, the integer part of that number is 0. So I write down 0. Then I multiply 0.376 by 2 again. So 0.376 times 2 is 0.752. Now the integer part there is 0, so I'm going to write down the 0 for my binary number. Then I multiply by 2 again, and 0.752 multiplied by 2 now is 1.504. And so now the integer part is 1 of that answer, so I write down 1. Then I take, and here it's important, I take the fractional part now. I ignore that 1. I take only the fractional part. I multiply that by 2, and I write down the answer, which is 1.008. So I carry across the 1. I multiply the fractional part by 2 again, and I get 0.016. So I copy across the 0. And so on and so on. I can do this indefinitely until either the answer, there's nothing left, the answer is 0, or I give up. So just like in the decimal number system, in a binary number system, you can have irrational fractions where the numbers just go on forever. And it was different numbers in different systems. So if you've got a decimal number that's only 3 decimal places, it doesn't mean that in your binary number you're only going to need 3 places. And in fact, you might need a number that goes on forever. So at some point you need to stop. So where you stop will depend on, you know, what the particular system is you're designing, how accurate the precision needs to be, or you just give up after 3 or 4 places if you don't mind. Okay? In an exam question or quiz question, I might say write it down to X number of decimal places, but if I don't, just, you know, do 3 or 4, something like that. All right, and then so I stopped here, I did 5 and I've given up, I've just stopped now. And I read off the binary part. So now this integer part that I stored at each step in the process becomes my binary number. And the one at the top is the most significant. And most significant means the one belonging to the highest weight column. So I'll talk a lot about, when we talk about binary numbers, we'll talk about the most significant bit, which is the bit on the left, because it's the one that corresponds to the highest weight, and the least significant bit, which is the one on the right, because that corresponds to the lowest weight column. Okay, so there is our integer part, and that's our number approximate. Of course, it's not exact, because I gave up after 5 decimal places, but approximately 0.188 in decimal is 0.00110 in binary. Okay? Yep. Yeah, so the most significant bit is the first bit in the number that you're writing down. So it could be a 0 or 1. And it also depends how many bits you assign. So normally you might say store this as an 8-bit number. And in which case, your most significant bit, even if the number is the same, so the number is 8, right? 1, 0, 0 is 0. If you're storing as a 4-bit number, 1 is the most significant bit. If you're storing as an 8-bit number, it will be 0, 0, 0, 0, 1, 0, 0, 0, in which case 0 is the most significant bit of the 8-bit version of the number 8. Does that make sense? Should have used a different example. Yeah, so the most significant bit is always the bit on the left. The least significant is always the one on the right. Easy way to remember it. So why does that work? Well, it works because when you multiply by 2, you're shifting one place to the left. Just like in a decimal number, when you multiply by 10, you're shifting one place to the left because it's a base 10 system. In a binary system, when you multiply by 2, you're shifting to the left, and when you're dividing by 2, you're shifting to the right. So equivalent situation in a binary number as in a decimal number. And you can actually use that fact if you want to do multiplication in digital circuits. If you want to multiply by 2, shift the number to the left by 1 spot. Multiply by 4, shift it to the left by 2 slots. Okay. But what we're using that to do now is we're shifting to the left, so we're moving each fractional part. So the fractional part here of 1/2, we multiply by 2, it gets shifted into the integer column. And that's how we know what the fractional part is. We multiply by 2 again, we're shifting the next part across. So the -2 component comes into the integer column and we're reading it off. And then we're multiplying by 2 again and again. So shifting each time so that the part we're interested in becomes in that integer column where we read it off. So that's why it works. You're welcome to use this method. If it's easier for you, you're also welcome to use, the first method we looked at, which is just to add up the numbers from the specific columns until you get the total that you need. Okay. All right, so now that we've done that, now that we've talked about how can we represent quantities with zeros and ones, we can go back, we can go back to our original problem of the analog to digital converter. So in the analog digital converter, I said you need to do sampling. You need to sample in time. In this case, there are 13 sample interviews for my grey waveform. And we need to quantize, so we need to pick, how many levels we want. In this case, we've got 16 levels. And then the final step, the third step, is the coding. And the coding is where we represent each level by a numerical value in binary. So in this particular case, I'm going to call this level 0. So it's binary 0, 0, 0, 0. This is level 1, so it's binary 0, 0, 1, so on and so on, all the way up to level 15, which is going to be binary 1, 1, 1, 1. So when I have this signal, I'm going to sample it. So I sampled it here. I quantized it, so I said, okay, the closest level is 6, and then I encoded it and I spit out 0, 1, 1, 0. So that's what your analog to digital converter does, those 3 steps. In this case, there are 15 levels because I have a 4-bit ADC. So with 4 bits, I can represent 2 to the 4 possible levels. When you buy an analog to digital converter, it'll specify how many bits. So n-bit, 2-bit, 4-bit, 8-bit, 16-bit. So if I have want to buy an n-bit analog to digital converter, how many levels can I have? 2 to the n levels, but the top level will have a value of 2 to the n minus 1, and the bottom level will have a value of 0. So there are 2 to the n possible levels. And the number of levels you have shows how fine you can do the quantization, which is why it's really important. If I just have a 2-bit analog to digital converter, I've only got 4 levels. And you can see with this waveform, if I only have 4 possible levels, it's not going to look anything like it when I do the analog to digital conversion. So the more levels, the more bits in my ADC, the more finely tuned I can do the quantization. But it also means the more data I need to produce and store and deal with as well, because now I've only got a 4-bit number being spat out by the ADC for every sample, whereas if I have a higher, so an 8-bit or a 16-bit or a 30-bit analog to digital converter, every time it does a sample, it will be spitting out 8 bits or 16 bits or 32 bits. Okay. So putting this all together, this is how we take the analog real world and we turn it into a binary representation of the world so that we can then process it inside our digital circuits. Any questions at this point? Okay. So we've talked about ADCs, analog to digital converters, and we've talked about binary number systems. So how do we represent our values with zeros and ones? While we're on the topic of number systems, I'm just going to mention the 2 others. If you have an old version of this PDF from Blackboard, I've just moved up 3 slides a little bit higher in the order, but these slides are in your PDF. All right, so we said you could use any number system you like, and one of the more common ones for us in this course is hexadecimal. So hexadecimal is a base 16 number system. Can anyone think why we might care about base 16? It seems a bit arbitrary that we would pick 16, right? Yep.
Because it's one of the binaries, it's 4 digits binary.
Exactly. The reason we pick it is because 16 actually happens to correspond to a 4-bit binary number. So what we can do when we use hexadecimal is we can use hexadecimal to do a shorthand notation of binary. Because you can imagine that binary numbers get quite long to represent even small quantities. And often they get very long, particularly when we start talking about the microcontrollers that we're going to look in the second half of the course. So it's an awful lot of zeros and ones to write down. So instead we write everything shorthand in hexadecimal. So that's why hexadecimal is popular for computer engineers. Okay, but it is a weighted number system just like any other, so it works exactly the same. Of course, we've run out of digits though. So we only use, in our Arabic numeral system, we only have digits for 0 through to 9. And we need to come up with some others, so they just happen to use A for 10, B for 11, C for 12, so on and so forth, up to F. Okay, now the weights are powers of 16. So 16 to the 0 is obviously the 1s column, the 16s column, the 256th column, and the 4096th column, so on and so forth. But now we have a lot more options for what we put in each column. It's not just 0 or 1 like it was with binary, and it's not 0 to 9 like it was in decimal. We can now use every symbol from 0 up to F. Okay? So, for example, if I have this hexadecimal number 1A to F, and again that little 16 subscript tells me I'm working in base 16. Exactly the same process to represent it as a decimal number as with binary, except that now we might have to do a little bit of multiplication as well. So I have one lot of 4096. I have A, which is 10 lots of 256. I have 2 lots of 16. And I have F, which is 15 lots of 1. And I add them all up, and the decimal representation for this quantity is 6703, so it's 6,703. So 1A to F in hexadecimal corresponds to a quantity which is 6,703. So exactly the same process as any weighted number system. Work out what the weights are for each column, and then work out, how many of each column's weights that you have based on the digit in that column. Alrighty, so if I shift to the left by one place a hexadecimal number, what am I multiplying by? 16. Okay. So bear that in mind. Later on, when we write numbers as hexadecimal to represent what's going on inside a microcontroller, and I say multiply by 2, some people will, without thinking, shift a hexadecimal number to the left one place. But that's not multiplying by 2, that's multiplying by 16. You need to, if you want to multiply by 2, you have to convert it into the binary and then shift it by one place, if that makes sense. That's something that comes up as a trap later. All right, so you can convert from hexadecimal to decimal and back again exactly the same way as we saw before for binary. And you can actually do the same thing for binary to hexadecimal, but there's an easy way to do it in hexadecimal because, like we said, one hexadecimal digit corresponds to 4 binary digits. So we can use that factor to our advantage to make converting from binary to hexadecimal really straightforward. So we break up our binary number into groups of 4, starting from the decimal point and moving left. So here we go, here's my binary number. I've broken it up into groups of 4. This particular group of 4 has only 2 digits in it, and I'll just zero pad. Like I said before, adding zeros onto the end at the left doesn't change the value of the number, just like it doesn't in our ordinary decimal numbers. So I'll add a couple of zeros. Now then, each of these groups of 4, I just write down what their value is in binary. So 1001 is 8 plus 1 is 9. 0110 is 4 plus 2 is 6, and that's obviously 1. F is the highest binary number you can have, which is 1111, and 3, and so on. So F is 15. And there I have my hexadecimal number. So I don't have to, I could if I wanted to, but I don't have to multiply through by the weights of each column. There's a really simple, easy way to go from binary to hexadecimal, and that's by grouping in 4s and doing each set of 4 bits into its independent, separate hexadecimal character. Okay. All good? Any questions? Nope. Okay, and then of course we can write that down with the little 16 at the bottom to tell us that it's hexadecimal. Although I didn't actually need to do that, the fact that there's an F in there is a dead giveaway that this is a hexadecimal number anyway. All right, and the other one is octal, which is a weight 8 weighted number system. So all weights are powers of 8. So we have obviously 1's column, 8's column, 64's column, 512's column, and works exactly the same way, except now it's powers of 8. So 3702 is our standard octal number. We can express it in decimal as saying 2 lots of the 1's column, no lots of the 8's column, 7 lots of the 64's column, and 3 lots of the 512's column. So 3702 in octal is equivalent to 1986 in decimal, so it represents the quantity 1986. Okay. And here's just a summary of the decimal, octal and binary for the first 15 numbers. Okay. So again, tutorial 1, we'll have a few questions there. You can practice going backwards and forwards in all of these. It's not technically difficult, but it just requires a bit of practice. All right, so those are the number systems that we're going to use. But computers need to represent a lot of things other than just numbers. Of course, they started out as computing devices, so numbers were the first things that they dealt with. But nowadays, of course, digital circuits deal with a lot more than just numbers. So the other main common thing that we want to do is type Word documents, for example, so we need to represent letters as 0s and 1s. And an alphanumeric code is a code that represents the alphabet characters as in binary. So the most common one that you may have heard of before is ASCII. And an ASCII is a simple 7-bit code. So that means that there's only 2 to the 7, or 128 possible characters that can be represented by this code. So it's a bit limited, which is why it's not commonly used anymore. But it was the first one and the most common one. So We take those 128 characters and we represent them by 7-bit code. If you need to store it in an 8-bit device, that's fine. You just put a 0 in the most significant bit and you have an 8-bit ASCII code. All right, so if you want to encode a character in ASCII code, we just use what's called an ASCII code chart. We find the character that we want, so let's say K, and we read off the row number, represent that in binary. We read off the column number, represent that in binary, and we write that down, and that's our binary value for K. So we use the numerical code for, what was it, 4? And the numerical code for, what was it, B? And so there's a 3-bit and a 4-bit, and we write that down, and there's our 7-bit ASCII value. Okay. Clear as mud? Have a go taking the word high and writing it down in ASCII code. So it's a capital H. There's a different code for capitals and lowercase, so you need the capital H and lowercase I. So all up, you'll need 14 bits, 7 bits for the H and 7 bits for the lowercase I. Alrighty, can anyone tell me what the H is? 1001000. Does anyone disagree? Great. So the H is row 4, and we're representing the rows by a 3-bit number, and 4 in binary is 100, and the column that the capital H came from was the 8th column, and we're going to represent 8 as a 4-bit binary representation of 8, which happens to be 1000. So our ASCII code for H is 1001000. And with I, we use lowercase I happens to be the 6th row. Binary for 6 is 110, and the 9th column, and the binary for 9 is 1001. So this is what your keyboard is doing. Every time you type into your keyboard, it is converting what key you happen to type into a binary code like this, and sending that binary code through to your computer so it can process it. Now, beyond ASCII, ASCII now only does 128 characters, and it only does the Latin alphabet that we're familiar with. And of course, there's more than just English languages out there, so there's a whole lot of different alphabets that might need to be represented in a code for computers to process. And that's where Unicode comes in. So Unicode has hundreds of thousands of characters, all specified with a particular code, and it's just a massive lookup table. So if you Google it, you just Google the character you want in Unicode, and it will tell you what the digits are for it. So for example, the capital A in Unicode happens to be this binary number, and as you can see, it's starting to get quite long. So when you actually Google A in Unicode, it will give you the hex. It will tell you that the binary code for A in Unicode is 0041. But what it actually means is the binary code is 8 zeros, and then 4 in binary, 0100, and then 1 in binary, 0001. So often, when you look up the binary representation of something, it will give it to you in hex, simply because it's a shorthand way of writing long binary numbers. And Unicode, of course, includes all of the emojis that we now have in our text messages. So every emoji has a Unicode assigned to it. So smiley face is 243A in hex. Okay? And every year they add a few new emojis and use up some of the free Unicode strings that they haven't yet assigned to anything. Okay, so this is how we represent things that aren't numbers as zeros and ones in computers. All right, but then there's many other codes out there So there's not many other number systems, ignore that. There's many, many other codes out there. For anything you might want to represent as binary, there's a code to do it. And I'm not going to go through very many of them. I'm just going to pick two that we're going to use in 1710 just to talk about them. The first one is grey code. So grey code is not a number system. It's not a weighted number system. It's not like binary or decimal or hexadecimal where you have weights to columns. It's just a code, just like Unicode. But it's a very useful code because you can use grey code to represent numbers in a way where you deliberately design the code so that as you go up in value, say from 1 to 2 to 2 to 3 to 3 to 4, the grey code changes in only one position. So if you have a look down this column, this grey code, we represent 0 as 0, 0, 0, 0, 0, that's fine. We represent 1 as 0, 0, 0, 1. So far that's the same as a binary number system, but that's where the similarity stops now. If we want to represent 2 in grey code, the choice, the specific code for 2 is 0, 0, 1, 1. And as you can see, it's not 2 in binary, it's just a code, not a number system. So this is a code for 2, and it changes in only one place from the code for 1. The code for 3 changes in only one place from the code for 2, and so on and so forth. So it's specifically designed such that as you count up, the code only changes in one place. And that's particularly useful when you're interfacing some mechanical systems with electrical systems. And so, for example, you might have something spinning and you're reading off values. And you might have like a transient change in, so the timing might be very tight, for example. And maybe if the number was 1 and you moved to 2, perhaps this bit might change a little bit more quickly than this bit, and your computer might read in 3 briefly before it reads in 2. And that can be a problem if you've got a time-sensitive digital circuit. Whereas if you instead use grey code, only one digit's changing at a time. So it doesn't matter how fast or how slow that digit, you're not going to get any incorrect digits in the transient if one bit changes a little bit more quickly than another. So that's what grey code is for. It's very useful in those scenarios. And it's also useful for us when we talk about counter maps later on. We're going to use grey code in that context. So the key is that a single bit changes between one code word in the next in the counting sequence. So any scenario where that's important, that's when you'll use grey code. The other one that we'll see in 1710 is binary coded decimal. Now, this is not the same as hexadecimal. Binary coded decimal, what we're doing here is we're taking the binary 4 bits at a time to represent each decimal digit, but we're not using a number system. So from 0 to 9, it's exactly the same as binary. You just represent 0 to 9 as the binary 0 to 9. So that's the same. The difference comes when you start to get more digits in your decimal number. So in my decimal number 10, I have 2 digits. I'm not going to convert that to the binary for 10. That would be binary number system. Instead, I'm going to convert 1 digit at a time into its 4-bit binary. So I take the digit 1 and I convert it into the binary for 1. I take the digit 0 and I convert it into the binary for 0. So if I had 99 in decimal, I would convert the 9 into the binary for 9, 1001. And then I convert the other 9 into the binary for 9, 1001. So it's not a number system. I can't add and subtract or do anything with these numbers. But it is useful in certain contexts, like, for example, doing a clock display. So on a clock display, I might want to separately encode each of the digits. So if it's 330, I'll encode the 3 with 4 bits, the other 3 with 4 bits, and the other 0 with 4 bits, and that will make sense for my clock display. I don't need to know on a clock display what the binary representation of 330 is. It doesn't make sense in that context. So I'd use binary coded decimal in that context and represent each digit separately, each digit of my time, separately as a 4-bit binary number. And we'll see this in when we build our circuit. We'll use a 7-segment display, which will use binary coded decimal to say what digit needs to go onto the display. So, for example, if I had the number 2469 and I wanted to represent it in binary coded decimal, I just separately take each digit and turn it into a 4-bit binary. And that's it, we're done. Not much I can do with it after I've done that, except, send it out to a clock. I can't do any maths or any processing with it. But in certain applications, it might be useful to represent a number using binary coded decimal. Okay, any questions? Yep. Here we go. Quick question. Why are these not valid binary coded decimal? How do I know those are not binary coded decimal numbers?
Because if you convert them to decimal, they're all 2 digits or more.
Exactly. They're all bigger than 9. And I know in a decimal number, the biggest digit I can have is 9. So if I try to convert that back, I'm trying to convert back f, for example, which makes no sense in a decimal number. So in binary coded decimal, there are some 4-bit patterns that are just not valid codes for binary coded decimal. And those are the patterns that correspond to any number bigger than 9. All right, question. I give you this 8-bit binary sequence. Is it A? Is it 65? Oh, not even a binary sequence. I haven't said base 2, have I? I just give you this string of zeros and ones. Is it A? Is it 65? Is it 1,000,001? Or is it 41? So which answer is correct? Multiple choice question. Anyone? Anyone want to take 41? Yeah? Anyone else? Something different? A? Yeah, you want to go with A? Okay. Say again? Exactly. I think you're hitting on the point there. If this was extended ASCII, it would be A. If it was binary, what would it be? Yeah. If it was decimal, what would it be? If it was binary coded decimal, what would it be? So, and I think that's really important. Depending on, if I just give you a strings of zeros and ones, if the context is not clear, it could represent anything. It could be a letter, it could be a number, it could be a grey scale value of a pixel in an image. Context is everything because there's so many codes and ways to represent the world as zeros and ones that you actually need to know which one you're using right now in order to know what the zeros and ones mean. So if you just pick up an arbitrary digital signal, put your oscilloscope on it and see a sequence of zeros and ones on your circuit that, someone's left a circuit behind, you pick it up, you turn it on, you put your oscilloscope on and you see a bunch of zeros and ones, you have no idea what that circuit is doing or what that represents unless you actually know which particular code or number system is being used. Right? So context is everything. And normally the context will be clear in this subject or it'll be explicit what context is we're talking about. And you'll need to do the same thing too when you throw around binary strings like this. All right, so we've looked at representing the analog world in binary. We've looked at representing numbers in binary. We've looked at representing letters in binary. And the next step is, computers need to make decisions. So we don't just need to add and subtract things or store Word documents. Sometimes we actually need to make decisions, do some sort of logical thought processes. How do we do logic in binary using zeros and ones? That's the question. And that's the remainder of this lecture. We're going to talk about that. How do we do logic using zeros and ones? All right, so a bit of definition first. So a proposition is just a statement which can be either true or false. Okay. So if I said the sky is blue, that is a statement, and that statement could be true or it could be false. Okay. So any statement that could be either true or false is called a proposition when we talk about logic. Okay, so proposition. Now, the goal of symbolic logic is to combine these kind of simple logical statements in order to derive other true logical statements. So you take a logical statement, which is either true or false, combine them all together, and end up with other more complex logical statements. So I think Bertrand Russell tried to do that And I think 3 textbooks in, he finally got to proving that 1 + 1 = 2. So it's not an easy thing to do, this symbolic logic, if you want to do anything, prove anything mathematical. But to make simple decisions, like do I turn the light on or off? Do I need to sound the alarm? Those kind of logical decisions we can do really, really well, and we will be doing those sorts of things in ELEC1710 using the binary 0 and 1 to represent true and false. Okay, so we can represent the logic that we're talking about either as a truth table or as a mathematical expression called Boolean algebra, which we'll get to next week. We'll talk about truth tables today. But let's have a look at an example. So I might make a statement which says, you will pass this course if and only if you are enrolled in the course and your final mark is 50% or more. So in that sentence, there are actually 3 propositions, and we're going to call them A, B, and Y. So proposition A, you are enrolled in this course. That is a statement that is either true or false. You are enrolled in this course. Proposition B, your final mark is 50% or more. That is a statement that is either true or false. It either is or it isn't. And then the final proposition in that sentence is you will pass this course. And again, that's just a statement that's either true or false. You either will or you will not pass. And here is the important bit. So we can, by defining these propositions, A, B, and Y, we can write down this sentence in symbolic form in this way. So Y equals A and B. So Y, you will pass this course if you are enrolled in this course and your final mark is 50% or more. Okay. So we are going to use this kind of symbolic form to write down combinations of logical propositions in this way, so that we can then turn it into digital circuits. So we can turn a statement like that into a digital circuit by using symbolic logic in this way. Okay. I know you guys won't have done symbolic logic before, so are there any questions? Pretty straightforward so far. Let's keep going. Okay, so this word and here in this sentence is actually doing all the work. That's the important bit. Both of those things have to be true. That and is the really important joining part, the really important logic operator on those 2 propositions. Okay. So these operators are what allows us to use symbolic logic to join propositions together. And the first one is and. Luckily enough, the and operator in logic works exactly the same as the word and in everyday English use. So it should be straightforward for you to understand the and operator. So and, by definition, the combination A and B is true if A is true and also B is true, and in any other scenario, it's not true. So if A is true and B is false, then the combination is false. If B is true and A is false, then the combination is false, because they both have to be true for their combination to be true. Because it's and. And means both have to be true. And so we can express this rule about how the word and, or how the operator and works, in something that's called a truth table. In a truth table, we write down all of our propositions. In this case, we had proposition A and proposition B, and we're not going to write down the full proposition, you are enrolled in this course, your final mark is 50. We're just going to write down the shortcut, you are enrolled in this course, your final mark is 50% or more. And then our final column is the output, our Y in our symbolic logic, A and B. So you will pass, Y stands for you will pass this course, which in symbolic logic is A and B. Now there's 4 possible combinations for whether A and B is true. So you might be, technically speaking, you'll probably say, well, how do I get a mark if I'm not enrolled in the course? But, leave that for now. You cannot be enrolled in this course and not have gotten 50% or more. You can be not enrolled in this course and have gotten 50% or more. You can be enrolled in this course and not have got 50% or more. Or you can be enrolled in this course and you have got 50% or more. So there's 4 possible combinations of those 2 propositions. And then the truth table says for each of those combinations, false, 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 true, true, false, true, true, what is the result after we apply the and operator. And remember, the result is you will pass this course if you were enrolled in this course, so if A is true, and you get 50% or more, so if B is true. So there's only one possible combination of those original propositions that will make the final proposition true, and every other combination makes the final proposition false. Okay. So while I'm writing down A and B in longhand right now, most of the time you'll see it written in short notation as A dot B, so the dot standing in for the and, or even quite simply AB. So just like in maths, you know, you might say x times y, you might just write it down as xy. In logic, where we want to say A and B, we'll just write it down as AB, and we'll know that stands for A and B. Or if you want to, for a while, you can write it out in full while you're getting used to it, A and B. Right, so let's look at an even simpler operator. So obviously a redundant statement, but let's say I had the rule that says you will fail this course if and only if you do not pass the course. Right? So here we have the propositions, let's call them Y, you will pass the course, and Z, you will fail this course. So we can write that in symbolic form as Z equals not Y. So if you pass the course, you will not fail the course. So that's basically what this symbolic logic statement is saying. If you pass the course, you will not fail the course. Okay? And this is what's called a not operator. So it's just the inverse operator, it's just the opposite. And the not operator only has one proposition as its input that it operates on. Let's call it proposition A. And it has the output proposition not A, which is actually just the opposite true or false value of A. So it's a two-line truth table for the not operator. If A is false, then not A is true. However, if A is true, then not A is false. So not is a logical operator. Works the same way as the word not does in English, which I guess is why that was chosen, in the sense that it does the opposite. So there are three ways to write down not. You can write it in full, Z equals not A. Other common ways is A with a bar across the top, so that's shorthand notation to say not A. Or A with a dash, which is used, for example, when you're using a typing and you can't put the bar in. So A dash is another way of saying not A. We will use all three of those as well in the course as, you know, whichever is the most convenient, and you can use whichever is the most convenient. Okay. So that was, we've done the and operator and we've done the not operator. And they're pretty straightforward because they mean what you would intuitively think they mean from English. Now, I'm talking about true and false, but of course, as we've laboured the point, we can only deal with zeros and ones, but that's easy enough. We just use convention and we say that false is represented by a 0 and true is represented by a 1. So 0 is false, 1 is true. This is called positive logic, but it's the usual. Of course, it's arbitrary which way you do it, but this is the usual common way, and this is the way we'll be doing it. So instead of writing down the word false every time, we'll just write down 0, and instead of writing down the word true every time, we'll just write down 1. So that now we can write down our truth tables that we saw before using zeros and ones instead of T's and F's. So what values are in this column for the truth table for AND? Starting from the top, working down, what zeros, combination of zeros and ones do I need to write in here? 0, 0, 0, 1. False, 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 true. Because both A and B have to be true if we want the output to be true. Okay. So whether we use T and F or 0 and 1, they're still called truth tables. And in practice, everyone just uses zeros and ones. Aside from introductory courses, you won't see truth tables written like this. You'll see them written like this. How are we going for time? All right, I'll take a quick 5-minute break and then come back and keep going on digital logic. Alrighty, let's get back to it. Okay, so we saw 2 logic operators so far, and not. And now we're going to look at OR. So a slight difference in or, in that there's actually two kinds of or, which is different from how we use the word or in the English language. So let me give you an example. If you rock up to a bar, the bouncer at the door might say you can come in if you're over 18 or if you're accompanied by a parent. So which scenarios there are you allowed in? You're allowed in if you're over 18, in you go. Doesn't matter whether there's a parent there or not. If you've got a parent, you're allowed in. Doesn't matter how old you are, in you go. And here's the important bit. If you're both over 18 and you happen to be there with your parent, you can head on in as well. So it's what's called an inclusive or. So when we say the word or there, we're including one or the other or both. So there are three scenarios in which you're allowed to head in through that door. Either you're over 18, or you have a parent with you, or you're both over 18 and you have a parent with you. All of those three are included in the use of the word or. So that's what we call an inclusive or. Now you might get up to the bar and the bartender might say, we've got a special on today. You can have a freebie. You can have a free drink, or you can have a free serve of chips. That's actually a different kind of or, isn't it? Because you can have the free drink, he'll give you that. You can have the free chips, he'll give you that. But you can't, in this case, have both. You can't say, I'm opting for the free chips and the free drink, thank you very much. So that use of the word or, even though he used the same word, or, was actually an exclusive or. So you could have the free drink, or you could have the free chips, but not both. So actually the same word there, or, is used for two different logic operations. And when we're talking about logic, when we're talking about digital circuits, we need to be very explicit about which one we're talking about. So we define two kinds of or. The inclusive or, which means includes the combination as a possibility that satisfies the or operator, and the exclusive or, which excludes the combination of the two possibilities as being an allowed condition. All right? So the inclusive or includes all three combinations. The exclusive or only includes the two combinations where it's one or the other, but not both. So we call those inclusive or and exclusive or. And in shorthand, we'll just write the inclusive or is or, and we'll write the exclusive or with an X in front of it. XOR stands for exclusive or. So inclusive or is true when A is true, or when B is true, or when both is true. The only time where it fails and outputs a false is when A and B are both false. All right, the exclusive or, on the other hand, is true when A is true, or when B is true, but not both. So the exclusive or operator will return a false when A and B are both false, but also when A and B are both true. Okay, so it's that fourth row over the truth table that's going to be different depending on whether we're talking about an inclusive or an exclusive or. So have a go. See if you can think what will be in the two columns of the truth table. For these, so these are our propositions, A and B, and they can be false, 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 true, true, false, true, true. Those are the possible combinations. What is the output of an inclusive or for each of those combinations? And what is the output of an exclusive or for each of those combinations? So can someone tell me the first one?
0, 1, 1, 1.
0, 1, 1, 1. Very good. Because if anything is true, if any one of the A and B propositions is true, the output is going to be true because it's an inclusive or. So all three of these combinations will give us ones, trues, as output. It's only when they're both false, so you're not over 18 and you're not with a parent, that you can't come into the pub. It's the only case where you can't get in, when both of the original propositions are false. So what's going to be different in the exclusive or? The last one, exactly. So the first three rows are exactly the same, it's just the last one. So you can't have the free drink and the free chips. That bartender's not going to let you get away with that. So that last row is different when it's an exclusive or. Okay? And again, shorthand notation, we're actually going to repurpose the plus symbol from maths, and we're going to use that for or. We're not adding. Okay? We're just repurposing that symbol to stand in for or. Okay? And we are going to use the plus symbol with a circle around it to stand in for XOR. That's the symbol we're going to use for XOR if we don't want to write it out using letters. So OR, we're going to repurpose the plus symbol, and XOR, we're going to use a plus symbol with a circle around it, and that's going to stand in for our exclusive OR. Okay. Alrighty, so that's the logic, and you can see how maybe we might build a circuit using these logic operators. So you might, for example, automate the bouncer at the door of the pub, and you might use a trust system where you say, are you under 18? Yes, no. Do you have a parent? Yes, no. Pop it into your digital circuit as a yes or a no, and then the door will either open or not, depending on the combination of propositions are true. So you can build digital circuits. Once you define these operators, you can build digital circuits to make the logic decisions for you. And you need to do that using circuit elements, which are called gates. So an AND gate is simply a digital circuit which does the AND operation for us. So we have two inputs, our logic propositions, A and B, and we're going to input a low voltage or a high voltage, depending on whether we think that that proposition is true or false. So if we have a low voltage, it means 0 or false, and if we have a high voltage at that pin, it means 1 or true. And then if it's an AND gate, it's going to look at that combination of voltages and output either a low voltage or a high voltage, depending on the rules of the AND operation. So you can see here that the AND operation will only output true if both inputs are true, both propositions are true. So that means an AND gate will only output a high voltage if both of the input voltages are high. So an AND gate is just a little circuit that does, using voltages, what the logical AND operator does in a truth table. Yep. And that can extend to any number of inputs. So you might have 3 or 4 propositions that all need to be true in order for the condition to be satisfied. So you might need to enter the pub, you might need to be wearing appropriate footwear and be wearing a shirt and be over 18. So there might be 3 things that all have to be satisfied to enter the pub, so then you would build that circuit with a 3-input AND gate. And they all have to be true for the output to be true for the door to open to let you in. So inside an AND gate is actually an analog circuit based on transistors. Now, if you continue on doing electronics in later years, you'll understand how this circuit actually does that AND logical operator, but it's not part of this course, you don't need to know. But inside that gate, which we're just going to purchase as a chip in this course, inside there is a little electronic circuit which is actually changing all the voltages around so that we achieve that AND operation inside the circuit. Not accessible, just in case you're worried. Same thing, a NOT gate. You can buy a little electronic circuit that does the NOT operation for us. So it performs the inversion. A high voltage at the input will become a low voltage on the output, and vice versa. And here's an example of a NOT gate, but this time using CMOS logic. So remember back on Tuesday I said the range of voltages that's considered as a 1 versus a 0 depends a little bit on the type of logic circuit that you're using. Well, the 2 types are a TTL circuit or a CMOS circuit. And it just basically means inside that gate, even though to you when you buy the chip it doesn't look any different, it means that inside there the elements that are used to create that logic are slightly different. They're using transistors or they're using CMOS logic. All right. And then, of course, you can buy an OR gate as well, which does, using voltages, the operation that we expect on a truth table for an OR. So that basically means if any of the inputs, any one or more of the inputs are high, the output will be high. And it will only be low if all of the inputs are low. And again, that can correspond to 3 or 4 or 5 or 6 inputs as well. As long as any one of the inputs is high, the output will be high. And of course, you can buy an XOR gate as well. Oh, I should have said, apologies. So this symbol here is how we'll represent the AND gate when we're drawing out digital circuits. So this flat line here with a curve will always, in a circuit diagram, correspond to an AND gate. This triangle with a circle at the end in a circuit diagram will always correspond to a NOT gate. When we want to draw an OR gate in a circuit diagram, we curve the input and it comes to a sort of a point at the output. That's an OR gate. And an XOR gate is just an OR gate with a double line here on the input. So you'll just get used to those different representations of those logic gates when you're drawing up your circuits. Okay, so an exclusive OR gate is just, again, another component. We'll buy it as a chip in the lab and you insert it into your breadboard. And then you'll input high or low voltages at the inputs, and then it will automatically create an output, which is either high or low, in exactly the same way as the truth table tells it to for an XOR. Okay. Now, an XOR can also be extended to multiple number of inputs. Little less obvious than with AND and OR, but if you say you have a 3-input gate, you have to look at it sort of pairwise. So you XOR 2 of them together, and then the result of that, you XOR with the third. And you can do it in any order and the result will be true. And 4 or 5 or more, you do the same thing. You XOR them in pairs and then XOR the answers until you get to your final answer. So that's how you would think about combining multiple XOR gates together for a 2-input, 3-input, 4-input, 5-input XOR gate. Alrighty. Now, we have those basic gates, but we can also start joining gates together. So we can have an AND gate followed by a NOT gate. And you can actually buy a pre-packaged chip that's already done that for you. It's already put the AND gate and the NOT gate together for you, and it becomes a NAND gate. But actually, inside the little package that you get, it's not actually putting together the circuit for an AND gate plus the circuit for a NOT gate. It's its own special circuit that does a NAND gate, and it happens to use slightly less silicon than using an AND gate by itself, which is why NAND gates, you'll see them used quite often, even though it might not make sense to you. Why are we using NAND gates? Why are we not just using, ANDs and NOTs? Well, the reason is because in terms of efficient use of silicon, it actually turns out that using NAND gates is a good idea. So that's why you'll see NAND gates quite a lot, even though logically we just think of it as an AND operation followed by a NOT operation. But you can buy them together as a NAND gate. Now, you might think the N, don't get confused, even though the N comes before the AND, the NOT doesn't come before the AND, it comes after. So a NAND gate is an AND followed by a NOT, not NOTs followed by an AND. All right, and the truth table for a NAND gate is easy. It's just the opposite of the truth table for an AND gate, because you just take the output of the AND gate and you invert it. And we write it down in symbolic logic, in shorthand notation. We write the AND, but to show that the NOT comes after the AND, we have to draw the bar, a solid bar across the top of all of it. And that shows us that the NOT comes after the AND. If we did a separate bar over the A and then a broken line with a separate bar over the B, that would be telling us that the NOT comes before. The NOT gates come before the AND gates. So it's really important not to get confused. It's really important actually when you're doing the maths to carefully draw those NOT lines, because that actually determines the order of the gates in the circuit, and it completely changes the function if you get it wrong. You can also use brackets, just like in normal maths. If you have a bracket, that means everything inside the bracket is affected. So if you can't use a bar and you're just using that dash for a NOT, you have to put the A and B inside the brackets and then put the NOT mark so that you know that the NOT goes across the entire A and B. Okay. Any questions? Okay, so far so good. And then same thing. You can have a NOR gate, which is basically just an OR gate followed by a NOT gate. So the truth table is you take the truth table for the OR gate and you flip everything. And again, when we write that down using our shorthand for symbolic logic, we write down the OR first. So remember that OR is represented by a plus. So A or B first, and then the NOT goes across the top of the whole thing to show that the NOT gate comes after the OR gate. Or we can represent it using brackets to say the same thing. And of course, there's an XNOR gate, which means it's an XOR gate followed by a NOT gate. And you'll see here that you can write this shorthand notation in a circuit diagram for OR followed by NOT. You can sort of squish them together and get rid of the triangle part and just have the dot at the output of the OR, and that represents an OR gate. Same thing for an and same thing for an XNOR. So you actually have to look pretty carefully when you're drawing digital circuits in a circuit diagram. These little circles everywhere change everything, so you need to watch out for them. So basically, this is an XOR gate followed by a NOT gate, and that little circuit there, that little circle there, that dot at the output of the OR tells you that this is actually an XNOR, not an XOR. Okay. And just as before, if you want to write down what an XNOR gate is, you just write down the truth table for an XOR gate and then just flip it. So it's the opposite. So everywhere that the XOR was a 1, the XNOR is a 0, and vice versa. And just like before, if you want to write down XNOR using maths or using symbolic logic, we write down the XOR first, remembering that the XOR symbol was this little plus with a circle around it, and we put the bar across the entire top to tell us that the NOT comes after the XOR gate. Okay, right, that's a lot of gates. Let's think about how we might actually now do some logic, might actually build some digital circuits to make decisions for us using gates. So, I need to build a digital circuit. This digital circuit is going to measure the level of water in 2 tanks, so tank A and tank B. And I've got a little sensor there that'll tell me if the level of water is above 25% or not. And if it is above 25%, I'll get a high or a true, logic true output from that sensor. And if it's below 25%, I'll get a low voltage or a false output from that sensor. Now I need to join a little alarm system. So we want to say green light means go, everything is okay. We want that green LED to turn on if both tanks are at least 25% full. So if both tanks are at least 25% full, we can, use our what is it? What would we be doing here? I don't know, our watering system. We can use our watering system with no problems if both tanks are above 25%. So the green light on means that everything is all operational in our watering system. Now, if we connect to a high voltage here and we have a low here, if we have a low voltage here, it means that current will flow. So this plus V just means we're connected to the maximum voltage. So that will be 3.3 volts or 5 volts, depending on whether we're using CMOS or TTL. But this is our high voltage, our plus V. If this voltage at the output of this gate is low, current will flow and the LED will turn on. However, if this gate outputs a high voltage, so equal to V, there'll be no voltage drop across this LED, so no current will flow, so the light will not turn on. So a low output from this gate will turn our light on as we require, but a high output from this gate will turn the light off. All right, so our circuit here is just a single gate. We can only use one gate to build our circuit. Which gate do we use? NAND, very good. Which gate do we use? We use a NAND gate. And how do you figure that out? You write down the truth table of what you want this circuit to do, and then you compare that to the truth tables for all the possible gates, and you can find the one that matches, and you can choose that gate. Or you can think of it, instead of doing that, you could just think of it logically saying, okay, if both are high, I need the output to be low. And every other case, I want it to be high. What is that? That's a NAND operation. So either way is fine, whichever works for you. Either write down the truth table for what you need and have a look at all the gates to find the one that works, or sort of do it logically and think about it, which is the second option only works if it's one gate. Once you start building more complex circuits, of course you're going to have to go the long way of drawing the truth table and working it out. Okay? Another example. I need to build a circuit now, which is an alarm circuit. So I have some windows and doors, and they all have sensors on them. And if the window or door is open, the sensor will output a high voltage. And if it's closed, it'll output a low voltage. And my alarm is going to go off if any door or window is open. Just one door or window open will be enough to set my alarm off. And my alarm will go off if my mystery gate outputs are high. So my alarm is designed so that if it gets a high voltage, the alarm will go off. So which gate am I going to use for my digital circuit now? Excellent. OR gate. Because if any of the inputs are high, I need the output to be high. So this is how I'm going to build digital circuits to do logic operations, to make decisions for me. I'm going to use symbolic logic to represent the decisions. I'm going to use zeros and ones to represent true and false. And I'm going to use gates to do the logic operations on those inputs to get the output that I want. And then if I want to do something complicated, I'm going to have to use a whole bunch of gates and join them all together, and we'll see how to do that later. All right. So one other thing, in what we've done here is we've talked about the circuit operating, and we know that there's only a number of possible combinations, right? There's 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on and so forth. So there's 8 possible combinations of windows open and high here. So that's 8 is probably as many as we can keep in our brain to figure out which gate to pick. When a circuit is more complicated, or it's not as easy as an OR, we might use something like a timing diagram to show all of the possible outputs for all of the possible combinations of inputs. So you could represent it as a truth table, but you could also represent it as a timing diagram. What does a timing diagram do? It tells you, so these are my inputs, A and B. Actually, in this case, I think I've just got 3 inputs. In this case, I've got 3 inputs, A, B, and C, and the inputs are changing over time. So at this point in time, all of the inputs are high. And timing diagrams become more important when we talk about sequential circuits. And in sequential circuits, what happens at a specific time point now can depend on what had happened in the past. So that's when timing diagrams become essential. In the circuits I'm talking about now, which are only take a snapshot at this point in time now and make a decision in this point in time, timing diagrams are only about as useful as a truth table. So either or, both are fine. But later on, they'll become more important when we start talking about sequential circuits. Okay, but let's have just as a practice, let's have a timing diagram. So in this particular example, I've given you a circuit, I haven't told you what it does, and you need to figure out what that circuit is. So you play around with the inputs, you change them to different combinations, and you measure the output, X, from that circuit as the inputs are changing around. Because you're going to try and figure out what this mystery circuit is doing, and I've told you it's just a single gate to make it easy for you. Pardon? A NOR gate? Any other guesses? NAND gate? Any questions? Yeah, it's a NAND gate. Because if you have a look, the only time where the output went low was when all of the inputs were high. And a NAND gate is the opposite of an AND gate. So an AND gate, the output will go high only when all of the inputs are high. And this one went low only when all of the inputs are high, so it's a NAND gate. Alrighty. Excellent. So here's a summary of all of the different kinds of gates. I didn't actually talk about these ones here because we don't really cover them in ELEC1710, but they are in your textbook. And what that basically means is we have a NOT on the inputs to the OR gate and the inputs to the NAND gate. I'm going to do some more stuff after this slide, so don't run away too quickly. Not quite finished yet. I want to talk about the lab for a few minutes as well. All right, so labs start next week. Please remember to do the lab induction. You can now start on tutorial 1, and you should be able to answer those questions. If you have any issues with tutorial 1, or this is, yep.
If I did a lab induction for the EE building last semester, do I have to redo one?
Great question. If you've already done it this year, you don't need to do it again. If you did it last year, you do need to do it again. Okay?
Is there a link for the lab induction somewhere? Or
there's not a, well, it's on your canvas. So if you go to Canvas, you should see, now where is it? This site. It's called CC Work Health and Safety. You should be automatically enrolled in that Canvas course, And all that course is the lab inductions and a safety and some other options, safety quizzes, things like that. All right. So what I'm going to do, guys, bear with me. Because labs start next week, I'm going to go through a little bit of the lab for those of you who may not have seen circuits before. So if you've done 1310 or you've built circuits for whatever reason somewhere else, you don't need to stay. I'm just going to talk about Ohm's law and current and not having the current to an LED too high to blow it up and things like that. So if you know all of that, you don't need to stay. But if 1710 is your first course here and you haven't built a circuit on a breadboard before, please stay. Okay, all right. So there's actually a wide range of... Guys, if you can just wait to talk till you get out, that'd be fantastic. Thank you. Because of the different programs that you guys are in, some of you will already have done digital circuits before, and analog circuits before, and some of you won't. So for those of you who haven't, I just want to go through some quick background, not assessed for this course, but nonetheless necessary for you to know in order to do the lab. So lab 1, the PDF is available on Canvas, and we're going to build a simple circuit, this circuit here, on a breadboard. Okay? And the breadboard's going to have a little power supply which we connect with the USB cable to the computer to power it. Now, the important thing I want to talk about here when we build this circuit is we're going to have a little LED, which is a little light, and the LED will turn on when current flows through it, and it will not turn on if there's no current flowing through it. And we're going to build a circuit like this, where we have VCCs, the positive voltage, and ground is basically the other terminal of the battery. Now, the important point here is why we need a resistor in this circuit. So, what you'll learn in 1310 when you do it is something called Ohm's law. And Ohm's law tells you V equals IR. So the voltage, which is this VCC, so 5 volts, 3 volts, is sort of the pushing power of how hard the electrons can be pushed through the circuit. And I, the current, is the flow of electrons, so how many electrons are flowing in. So, electrons per second, for example, is the current. Now, so the higher the voltage, the higher the current. The lower the voltage, the lower the current. But it's proportional to, remember I said V equals IR, R is the resistor. So if you put a resistor, if you keep the voltage the same, so let's say 3 volts, you stick a resistor in there, it slows down the current proportionally, V equals IR. So if with 5 volts, if I have a 1 ohm resistor, I get 5 amps current. Okay? If I increase the value of the resistor, so for example I have a 10 ohm resistor now, I get half an amp of current. I get less current going through. So as I change the value of this resistor in this, so current is going to flow from the positive terminal of my source, whether it be a battery or whether it be the breadboard, this little breadboard source here. Current is going to flow from the positive terminal through to the negative terminal and back around. And the amount of current that's going to flow is going to depend on this resistor value. Because we assume that the little LED, the little light, has no resistance. It's so low that we just assume it has no resistance. The important point is you have to have that resistor in there, because if it's not there, too much current will flow and the LED will be damaged. It won't work anymore. And that's true whether we use this single component LED in lab 1 or whether we use the 7-segment display later on in later labs. 7-segment display is just 7 LEDs connected together. You have to have a resistor in the circuit for each LED. So many students forget that bit or don't know because they haven't done 1310 and they destroy the components. Okay, so you need to be careful about that. And the other thing I would say is we're going to be building a circuit on a breadboard. If you haven't used a breadboard before, of course the demonstrators will be there to help you, but if you want to get a little bit of experience before you go in, I recommend Tinkercad. So this is just a free online software program where you can build all the circuits we're going to build in 1710 and try it out and see, blow up components, figure out which way things have to face, figure out how the lines of the breadboard are connected together. So you can't see it, but underneath this breadboard, there's a piece of wire connecting all of these 5 pins together. So if I, for example, put an LED, let's say I put an LED here on this column, and I connect up the positive of my battery to this point in my breadboard, then what I've actually done is connected the LED to the power supply. I can't see that connection because it's happening in underneath the breadboard, but that's what I've done. So all of these 5 are connected together. There's a gap in the breadboard, which is a dip in the plastic, and then all of these 4 are connected together. Okay? And then all of these 4, these 5, these 5, these 5. Okay? Now, yep.
Sorry, what did you say that website was called?
Tinkercad. There's a link to it in the PDF for Lab 1. So in the PDF to Lab 1, there's a link to it. And so so for example, if I want to try and build that circuit that we just saw in the lab, I've got the only thing that Tinkercad doesn't have is the exact same breadboard power supply that we're using, but I'm just going to use this 3-volt battery instead. I connect the positive terminal of the battery to the positive row of the breadboard, and you see that red line running across there, and you'll also see it as you hover over. It means all of these little holes in the breadboard are all joined together. So if I connect the power of my battery to this row, I basically can connect a circuit component to any one of these pins, and I'll be connecting it to V-volts. Similarly, if I connect a wire down here, this row here is my 0 volts, and if I want to complete the circuit back to 0 volts, I just connect a wire to here. So let's do it. I've got my battery, powered it up, so let's connect back down and close it. So I've gone from the battery to the LED, through the LED back to 0, so current should flow. Maybe. Okay, nothing happened. The reason it didn't happen is because these LEDs are directional. So I need to take that out, I need to turn it around, and I need that short kinked part of the LED, to be connected to the positive terminal of the battery, not the longer leg. Now let's try it. Excellent, it's turned on. But what did I forget? Exactly, and it's telling me that, right? It's going to tell me current through the LED is too much. So it's calculated that there's a nominal resistance value for that LED. It knows the voltage, it's 3 volts. It's calculated how much current's going through, and it's telling me it's too much. So then let's put a resistor in. Now resistors are not directional. They can go any way, up or down, it doesn't matter. Let's choose a resistance, so 1 kilo ohm in this case. And then these 2 pins of the resistor are not joined together because I'm bridging across that gap in the breadboard. But these pins are all joined together, so now I can join to ground. All right, let's turn it on. And now it's turning on without breaking. And it can tell you how much current is going through. Oh no, it doesn't tell you. Yep.
Do resistors have to bridge the gap?
No. I could do something else. Good question. I could stop simulation. Give me a sec. I could spin it round. And I could have done that. Now I have to have one of the terminals in here so it connects to the LED, and then I could have done something like, this is going to get messy, but let's say I did that. That will also work. And same thing on the breadboard when you build it in the lab.
Cool. Put it on the other side.
Pardon?
Could you put the resistor connecting to the positive input of the LED?
Yep, you absolutely could. So the resistor can be either side, it's totally fine. So I could connect it like this, and do something like this. So the order, it's a very good question, the order doesn't matter. What did I do wrong? Oh, yeah, this is actually a very common problem in real breadboards too. You've got to get it all lined up. Very good, thank you.
Sorry, what was the problem there?
I joined it to the wrong column. I joined it to column 10 instead of column 12.
Why does that matter?
Because only these holes are connected together. This hole here, I had something like this, for example. So this pin here is not connected to this pin here.
But it's connected to the one next to it.
It's connected to the one above and below it, yeah,
Oh, okay, yeah.
but not to the one either side.
Right.
Yeah, it's only connected to the ones above and below. So that's why I did it wrong. I had to have it in the same column in order to be connected to the resistor. Otherwise, there's like an open in the circuit and no current can flow over an air gap. It just, you know, everything needs to be connected together for current to flow. Yeah?
Are the positive and negative rails on the top and bottom connected?
No, they're not. So you can use both of them. So for example, I could, you know, bridge this gap and now they're connected. Now I have positive on both of them and I could do the same thing with negative. If I needed lots of negative pins, I could connect them like that, or I could connect them both to the battery either way, and then they would be. But inside the board, no, they're not. All good? And then the other element we're going to add is a push button switch. These ones you actually do need to put across the gap. And what the switch will do will allow you to turn the circuit on and off without actually disconnecting the power supply, putting it in and out, just by wiring up the lines on the pin. That's just a push button. Yep.
Why do you have to put it across the gap?
Because I didn't want to tie these pins together. And also in the actual breadboard, it only fits there. But you've got to get it right. So have a look in the data sheet. You've got to get the right orientation of it to get the right circuit. Play with it in Tinkercad because it'll tell you when you get it wrong. And then there's also other things that we'll use later on, not in the lab next week, but there are other, you know, things. There's a 7-segment display in here somewhere that we also use in the lab. There's a 7-segment display. There are other components. So you can practice all of the labs beforehand if you want to. Okay, any questions? Okay, wonderful. Enjoy the labs next week.